Hello everyone, welcome to this third lecture on semiconductor electronics. In today's class we shall discuss about the intrinsic and extrinsic semiconductor. If you remember the last class we ended with this particular slide where we divided the semiconductors into two categories. One is the intrinsic semiconductor, another is the extrinsic semiconductor. Where already I told that intrinsic semiconductors are those categories of semiconductors where you have got the number of holes to be exactly equal to the number of electrons, or at least nearly equal to the number of electrons. Whereas on the other hand, the extrinsic semiconductors can be further divided into two categories. One is p-type, another is n-type. The prime characteristics of extrinsic semiconductor is that you do not have the equality between the number of holes and electrons. If the number of hole is more than the number of electron, in that case we call it to be p-type semiconductor. And if the other way around, that number of electron is greater than the number of holes, then it is called the n-type semiconductor. Alright, so in today's class we shall discuss in little bit more detail about the intrinsic semiconductors and the extrinsic semiconductors, so as to say how exactly the p-type and n-type semiconductors can be made, how they are fabricated, or maybe how exactly we can add some impurities to the intrinsic semiconductor and we can generate extrinsic p-type or n-type semiconductor. Let us start with intrinsic semiconductor. A pure semiconductor which is free from every impurity and have the number of holes and electrons to be the same is called intrinsic semiconductor. If definition arrives, in that case you have to write these particular lines. So what we have understood from these lines, that a pure semiconductor, intrinsic semiconductor means a pure semiconductor. That means by purity we mean that there is no other material present. For example, it is an intrinsic semiconductor of silicon, then I would expect that other than the silicon atoms there are no other atoms whatsoever amount is present in that crystal. Similarly, if you have germanium intrinsic semiconductor, you have only germanium atoms and nothing else can be present even in a single bit. Alright. So germanium and silicon are the most common type of intrinsic semiconductors. Both germanium and silicon has diamond-like structure. This is something which you have to remember. It's quite important. And in each of this structure, like germanium or silicon, each atom is surrounded by four nearest neighbors. Germanium and silicon have four valence electrons. In its crystalline state, each germanium or silicon tend to share one of its four valence electron with each of its four nearest neighbors. For example, exactly how or what does it mean? For example, germanium, it has got a valency of 4. Valency 4. Silicon has also got a valency of 4. 4 why? Because you remember in the silicon structure, the last outermost orbital shell, we wrote 3s2 and 3p2. That means in the outermost shell you have got 2 electrons and 2 electrons, that is total 4 electrons, out of which the 2 electrons are in the s orbital and 2 electrons are in the p orbital. But whatever, ultimately 4 electrons are there in the valence shell, that means in the outermost orbital. So both germanium and silicon, they have 4 electrons in their outermost orbital and they require another 4 to complete, another 4 to get the inert gas structure. Why? Because you can see the outermost orbital in case of a silicon is 3p2. So it requires, but p orbital can require or accommodate another 6, I mean total 6 electron, out of which 2 is there, so another 4 is required, so that 2 plus 4 becomes 6. So that is why both germanium and silicon require another 4 electron to get the inert gas structure or stable structure. So what it does, suppose this is a germanium atom, this is a germanium atom, here is another germanium atom, here is another germanium atom, and here is another germanium atom. Okay, so this germanium already has 4 electrons in its neighborhood. Although I am showing it with germanium, the same thing happens even in the case of silicon, as already has been shown in this particular diagram. So now this germanium atom will have another 4 electrons like this. Okay, so this germanium will also contribute an electron here, here, here and here, and similarly all other germanium atoms will contribute their electrons. So as to say that each germanium atom has got 4 outermost orbital electron. Now see, for this particular germanium atom which is at the center, it has made a covalent bond between these, between these, between these and these. Now how many electrons this germanium atom is getting? Total 8. See, 2 plus 2 plus 2 plus 2. Total 6. Total 8. These two, these two, these two and these two. Total 8 electrons it has got. So 4 already it had, and 4 it has acquired by forming covalent bond with the near neighbor germanium atoms. Got it? So similarly, every germanium atom will have its nearest neighbor, and ultimately it will contribute, or it will acquire the required number of electrons, which is 8 in its outermost shell. Got it? This is how they are bonded in a covalent sense. The same thing also happens in case of a silicon. Here it is shown, this silicon atom which is shown at the center of attraction, suppose it has already been it has already acquired 8 electrons by forming covalent bond with the nearest neighbors silicon atoms. All right, so this kind of structure is formed by germanium or silicon. All right, now what happens if you bring down the temperature at 0 degree Kelvin? At 0 Kelvin temperature, for germanium, although I have written, this is not only for germanium, it happens even for silicon also. So at 0 K temperature for germanium, the valence band is full. As you can see in this particular diagram, the valence band is completely filled. The conduction band will definitely be empty. The energy gap is 0.72 electron volt, and the conduction band is totally empty. So we know that in case of semiconductor materials, we have two distinct bands. One is a valence band, another is a conduction band. So the valence band at 0 K temperature for the germanium is completely filled, conduction band is completely empty, and the forbidden band or the forbidden gap has got an energy of 0.72 electron volt. Alright. Now since there are no electrons in the conduction band at 0 K temperature, hence germanium at 0 K temperature behaves as an insulator. Now this is a very important question which may be asked during your examination, that why semiconductors behave as insulators when temperature is brought down to absolute zero. The reason is, when the temperature is brought to absolute zero, all the electrons they lose their energy and ultimately they come down to the valence band, and they acquire their definitive positions in the valence band, and there is no electron available in the conduction band. As a result, the conduction band is empty and the valence band is filled. Hence, since there is no electron in the conduction band, there is no conduction or conductivity possible, and that is the reason why semiconductors behave like an insulator at absolute zero temperature. So conduction is possible only if some covalent bonds are broken. Now what happens at absolute zero? We have understood that this is behaving like an insulator. Now if you add some external energy from any source, it could be from light, it could be via electricity, it could be via any other mode like heat. So from any kind of a source, you have from any external source, if you provide some external energy, what will happen? Some of the covalent bonds in the valence band will be broken. And if the bonds are broken, some amount of electrons will be released. That is a notion that we have already learned, that whenever electrons are released, then there must be some bond to be broken. So electrons will be released and they will move to the conduction band. So some of the bonds in the valence band will be broken, electrons will be released, and those electrons, if they acquire enough energy to jump from the valence band to the conduction band, in that case they will move to the conduction band. Okay, so in that case there will be conduction possible in the case of germanium or silicon in the intrinsic semiconductor. The minimum energy required to break a covalent bond is 0.72 electron volt in the case of germanium and 1.1 electron volt in the case of silicon. So for silicon, this gap happens to be 1.1 electron volt. These two data are very important. You please remember this. Okay. So for an intrinsic semiconductor, NH, the number of holes, must be equal to number of electrons, which is ultimately equal to the number of intrinsic carrier density, because this is something very important. Ni means intrinsic carrier density, because that's what means, since number of holes and number of electrons are the same, so you need not to call separately as okay, this number of electrons or this number of holes are present in intrinsic semiconductor. You can just call it to be intrinsic carrier density. Okay, if you just give intrinsic carrier density, which is equal to Ni, then we will automatically know that okay, these many electrons and these many holes are present. Okay, so with the increase in temperature, larger number of electrons will be able to cross the barrier of forbidden gap and move to the conduction band, and this will leave equal number of holes in the valence band and equal number of electrons in the conduction band. All right, so this is all about intrinsic semiconductor, that when you apply some external energy, the bonds in the valence band will be broken, electrons will be liberated, those liberated electrons will cross the band gap and will go to the conduction band. So you have equal number of electrons, suppose n number of electrons are there in the conduction band, similarly n number of holes will also be created in the valence band. Because why? Because absence of electron in the valence band is a hole. So those electrons which moved from the valence band to the conduction band, they will all leave behind a hole in the valence band. Okay, so that is why number of electron and number of holes in the valence band are equal in the case of intrinsic semiconductor. All right, so although I have shown it for germanium, for silicon also the fact is same. So in the next figure you can see something. For example, here you see initially every silicon atom was bonded very nicely, but from certain source, this light source will come, this will break a bond, this electron becomes free and it roams all about, and after some time the electron loses energy and again get captured by the hole. You see, this is a hole which has been created because the electron has been moved out. So similarly, from one single bond, if an electron is moved out, in that case what you have? A hole created at that location. Right? So here, although we have shown that there is an external source of light which is responsible for this bond breakage. All right, now this is without electric field. What happens if you apply an electric field across this kind of thing? If you apply an electric field, what will happen? Suppose there is a gap, then the near neighbor gap, suppose here you can see all the electrons are filling up this gap. For example, the whole location is filled up gradually. Because this is positive, so electron will move in this side like this, holes will move in the opposite side. So hole moves in the opposite side means what? Actually electron move from the near neighborhood to a hole, and that is why it gives you an impression that holes are moving on the opposite side of that electron. Okay, this picture is a very nice representation where you can see that electrons from the neighboring bond or neighboring orbit, they are filling up the hole. You can see there are 8 electrons all across the silicon, and you can see that very gradually a whole location is being filled up by the electrons. So electron move towards the positive terminal of the battery, and as if the hole moves away from the positive terminal of the battery or moves towards the negative terminal. All right, so this picture gives a nice illustration. Now how about the current? Current you will get only when you apply an electric field. So total current equal to sum total of electron current plus the hole current, IE plus IH. Okay, as we all know, in case of semiconductor, both holes and electrons, they carry electricity. So that is the reason why total current is not given only by electron current but also hole current. Now extrinsic semiconductor, and as we all know, for making an extrinsic semiconductor you have to dope means adding some amount of impurity. So a doped semiconductor or a semiconductor with suitable impurity atoms added to it is called extrinsic semiconductor. Now there are two types of extrinsic semiconductor. One is called N type, another is called P type. How we can make N type? See, pentavalent means the valency is equal to 5. Now we know intrinsic semiconductors such as germanium or silicon, they have valency 4. All right, that means they have 4 extra electron or outermost electrons in their outermost orbital shells. Now pentavalent atoms such as arsenic, antimony, phosphorus, etc., they have 5 valence electron. That means 5 electrons in their outermost orbital. So when you add those pentavalent atoms to intrinsic semiconductors such as germanium or silicon, the resulting semiconductor is an extrinsic semiconductor, and that is called N-type extrinsic semiconductor. Why it is called N-type? We shall come to that in a while. Similarly, if you add trivalent impurity, trivalent means whose valence is 3. In that case, you get P-type semiconductor or P-type extrinsic semiconductor. So what are trivalent impurities? These are indium, boron, aluminium. Now remember, silicon and germanium are intrinsic semiconductors and they belong to the group 4 of the periodic table. Okay, whereas the pentavalent atoms or pentavalent impurities, they belong to the group 5 of the periodic table, and similarly the trivalent atoms, they belong to the group 3 of the periodic table. One important thing is that while making an N-type, we are doping impurity having valency 1 plus than the intrinsic semiconductors. And while making a P-type semiconductor, we are doping impurity whose valency is 1 minus than that of the intrinsic semiconductor. So that is why here valency is 3 and here valency is 5. It is 1 plus than the intrinsic, that is 4 plus 1 is 5, 4 minus 1 is 3. What is the reason for that? That is very interesting and it will be clear in a while. Now before we go into that, let us try to understand what is the meaning of doping. Okay, now doping is a process of deliberate addition of a desirable impurity atoms to a pure semiconductor to modify its properties in a controlled manner. Okay, and in the case of doping, the number of impurity which are added is very less, almost how much? That 1 in 10 to the power 10. Okay, if you have 10 to the power 10 silicon atoms, then out of that one atom will be a doped atom. For example, if it is a pentavalent atom or trivalent atom, whatever you wish you can dope, but 1 in 10 to the power 10. So see, the doping amount is so less. All right, but that small amount of doping increases the electrical conductivity of a semiconductor to a significant extent. Okay, you can't believe to what extent this increases. Doping increases the conductivity of semiconductor to a large extent. All right, that is the reason why doping is important. Now let's come to the details of making an N-type or P-type. Now look in the picture which are given over here. Okay, I also would recommend that you please go through these lines completely one by one, and I will just explain what actually happens in case of doping of a pentavalent atom. Now let's say pentavalent atom is phosphorus. Phosphorus has got a valency of 5. Now what happens when you add phosphorus to a germanium or silicon? I have although shown only germanium crystal over here, but this is also equally valid for silicon. Okay, so what happens when you add phosphorus impurity? Phosphorus is pentavalent, that means it has got 5 electrons in its outermost shell, but out of that 5, germanium requires only 4 electrons to make a covalent bond. So that is why 4 of the electrons of phosphorus makes covalent bond with germanium. See, 1, 2, 3, 4. So these 4 have made a covalent bond. But 1 electron will remain as an extra because phosphorus can give you 5 electrons, out of which we have taken 4 electrons to form the covalent bond with germanium, because germanium requires 4 electrons to form covalent bond. So 1 electron is extra, 1 electron remains as an extra quantity. And this electron, interestingly, is very loosely bound because this is not a part of any covalent bond. This is only bonded to this phosphorus nucleus. So hence it is very loosely bound, and with a small addition of energy, this electron will be free to move about. All right, and that small addition of energy is very small indeed. Almost you can see 0.05 electron volt for silicon and 0.01 electron volt for germanium. So that is why even in the low temperature, not even low temperature, you can say just room temperature. Okay, in the room temperature, that is standard, we take it to be 27 degrees centigrade or 300 Kelvin. There itself this particular electron is completely free. This is no longer bonded to this phosphorus. So this extra electron behaves as a free electron. This is free to move anywhere, all right, and hence the conductivity actually increases. And since the carrier here is the extra free electron which is carrying a negative charge, hence from that negative charge we call it to be n type semiconductor, because you have got additional electrons, and electrons have got negative charge. So that is why from negative charge to n which has come, so we call it n type semiconductor, all right. And electrons, that is the reason why in case of an electron n-type semiconductor, electrons are the majority charge carriers. Now why the concept of majority charge carrier? The concept is important because although we have got rich, because see, this electron is given by one single phosphorus. Now you will definitely not add a single phosphorus only. In a crystal you will add more numbers of phosphorus, at least if you even count at 1 in a 10 to the power 10, even then you will have lot many phosphorus atoms to be added, because doping is generally very small. For example, 0.05% of the original atoms you dope, but at least even then a significant amount of phosphorus atoms will be there, and each of them will contribute one single electrons, all right. So that electron will behave as a free electron, and that is why you have a large availability of free electrons into the crystal. However, you cannot deny the existence of holes. For some reason, there may be some electrons from this valence bond will be broken, because at room temperature also it is quite possible that some of these valence bond will be broken, or maybe from some other reason, from external source of energy these bonds will be broken, and these valence electrons, these are the bonded electrons, they may also be liberated. So if they are liberated, they will leave behind a hole. Remember, this electron is a free electron. So if this electron moves, it will not leave behind a hole. It will never leave behind a hole. Holes are generally left by the electrons which are bonded or which are liberated by the breaking of a bond. All right. So there could be a process, or there could be a situation where these electrons will be broken and you will have a hole. So that is why, although we have got majority of these electrons in the n-type semiconductor, but holes also may be there in a small proportion. So that is why we call electrons are the majority charge carrier in case of an n-type semiconductor. However, holes are the minority charge carrier, because we cannot deny the existence of holes. All right, there may be some kind of crystal defects, there may be some kind of manufacturing defect because of which a hole might be there, because of which maybe that there is one covalent bond which is incomplete. So that is the reason why holes can be there. All right, so that is why you call the electrons to be the majority charge carriers and holes to be the minority charge carrier in n-type semiconductor. All right, exactly the opposite which happens in case of p-type semiconductor. Now in p-type semiconductor, you dope it with boron, which is a trivalent. Trivalent means it has got 3 electrons in its outermost shells. Now 3 electrons means, now germanium require 4, but boron can only give 3. See, boron has given this one and this one. So it also required an electron here, but it is not there, because boron can give only 3 of which has already made a covalent bond with the near neighbor atoms of germanium, but this germanium atom remains thirsty. Why it remains thirsty? Because it requires an electron, but it is not getting it from boron. So this location or this bond is incomplete. This is called an incomplete bond. All right, incomplete covalent bond. So in an incomplete covalent bond, the region of absence of electron is nothing but a hole. So that is why in p-type semiconductor you have availability of holes and not the electrons, right? That is why in case of p-type semiconductor, holes are the majority charge carriers and electrons will be the minority charge carriers. All right, so that is the difference between p-type and n-type semiconductor. Okay, I recommend once again to go in between lines here. Okay, these lines you please go through. Now in a doped semiconductor, the number density of electrons and hole is not equal, definitely, because you have doped it. So in n-type, electrons will be more, in p-type holes will be more. But there is a relation which is maintained at thermal equilibrium, and that relation is given by, for any extrinsic semiconductor, the product of the electron and the hole density is equal to the square of the intrinsic carrier density. Ni is the intrinsic carrier density. Alright. Now this relation is very important in the case of extrinsic semiconductor at thermal equilibrium. You may be asked to do some numerical problems based on this relation. So this is an important thing, please do note it. Alright. Now this is the last slide of today's lecture. Let us also differentiate between p-type and n-type on the basis of energy band diagram. Now let us further understand what happens exactly whenever you add some electrons to the n-type and you add some holes to the p-type. Okay. So let us first go into the p-type. In p-type, for silicon semiconductor, the doping of trivalent impurity atom produces some extra allowed energy level which are situated in the forbidden gap slightly above the valence band. Now what happens? Till now we had the notion that in case of a intrinsic semiconductor there are two bands only. One is a valence band, another is a conduction band. But as soon as you dope with trivalent impurity, because you are going to make p-type semiconductor, so you have to dope it with trivalent impurity. So once you dope it with trivalent impurity, another energy level gets created in between the conduction and the valence band. Now remember, in between conduction and the valence band, this is the forbidden gap. Okay, so this part happens to be the forbidden gap. This part, this is forbidden, nothing can be there. But nothing can be there in the case of intrinsic semiconductor. When you dope it with trivalent atom, there is an extra energy level which gets created over here. As a result of this, the electrons which are already there in the valence band, they get it easier at some flicker of energy, even at room temperature. These electrons leave the valence band and like to sit over here in the new level. Alright. The electrons will sit in this new energy level. Since the electrons go from the valence band to this new energy level, they will leave behind some empty spaces which are nothing but called holes. That is the reason why you have majority charge carrier as holes, and this new level which is created is called the acceptor level. Acceptor level, why do you call it acceptor? Because it is accepting the electrons from the valence band, so you can say it to be acceptor levels. Alright, so this is the new energy level which is created and it is called acceptor level. So electrons will leave the valence band at room temperature because that amount of thermal energy is sufficient for this electron to leave the valence band and go to this new level, and hence it will leave behind holes in the valence band, and it ultimately will get majority holes in the p-type. In the n-type semiconductor, something extra happens. In the n-type semiconductor, because you have doped it with loose electrons, because pentavalent atoms you have doped in with, and ultimately in pentavalent four valency atoms, four valency electrons, they will make covalent bond with the germanium and one will remain as an extra. So that will give you a new level just underneath the conduction band, and this is called the donor energy level. Why it is called donor energy level? Because here electrons are there. The loose electrons which were there, those loose electrons of the pentavalent atom remains in this donor level. So whenever you give some small amount of energy, thermal energy, even at room temperature, these electrons get sufficient energy to cross and cross the small barrier. The barrier becomes so small now. So these electrons go directly to the conduction band, and ultimately they conduct electricity, because in order to conduct electricity by electron, you need to have electron in the conduction band. So that is why donor level is called, because donor level means the energy level which supplies electron to the conduction band. That is why we call it donor level. All right. And consequently, the atoms, the impurity atoms which provide electron in n-type, they are known as donor atoms. In the case of p-type, since the impurity atom, they accept electron and ultimately uh, I mean makes hole in the valence band. That is why they are called it acceptor atoms. All right. So this is all about the details of p-type and n-type semiconductor on the basis of energy band diagram. These things are little bit new to you, I can understand that. So I would suggest that you please go through these slides carefully. I mean, go through the lines very carefully. If you do not understand, go again and again, stop the video and see it many times. And if you have still problem, in that case, please revert back to me. All right. So thank you for today.